Welcome back, everyone. We have reached the end of Unit 1, the atom, and we are going to be discussing how to attack this practice test. Okay, so let's get started. Number 1. Keywords here is the elements that they're giving you and that it's in the excited state. So I'm going to go to the reference table and look for potassium. So I'm going to find potassium over here, the K, and the electron configuration of potassium I'm seeing is 2881. So if I go back to my question, 2881 is option C. So I am going to actually cross that out because that is my ground state. That is not excited, so I can do that. Now I'm going to look for the one that it doesn't change the number of electrons. So that's out, A and B, and all I'm left with is D. D is showing me that one electron went from the third orbital to the fourth. So one jumped from here to the next. It doesn't change the number of electrons. 2 plus 8, 10, plus 7, 17, and plus 2, 19. And same thing over here is happening. Does not change the number, so D is our answer. Number 2, this is talking about the very specific number we have in the periodic table. So it's talking about this number right here. This number, if you do not know what it's called, look back at your key at the center of the periodic table. That is called the atomic mass. So that answer would be A. Atomic mass of an element, that's the weighted average of the atomic masses of naturally occurring isotopes. Number 3, which one is hydrogen isotopes? I should first look at the symbol. If the symbols are not representing hydrogen, then right then and there I can cross it out. In this case, all of them are H, so I can't cross out any based on the symbols. Now, going back to the review sheet, if you go to the third page shows you what goes on the bottom left and on the top left. So on the bottom left, we have the number of protons in the bottom left. That is what the number represents. And on the top left, the mass number. So let's go back to the practice test. I'm looking at these and I see that there is some that have different numbers and some that have the same numbers. Now, if I go to the reference table and I look for hydrogen, hydrogen only has one proton. So I should be looking for the one that has 1 as the atomic number, so the bottom left number. I go over here and I see that A has the bottom left number as 1 for both isotope notations. And looking at the other ones, I see that 1 has a different number, so they're not equal. Once you start changing the number of protons, that means that you're changing the element. So B, C, and D do not make sense because the number of protons are different. So A is our answer. Number 4, what is the mass number of this? So they give you this information. So you need to be able to know what does that top left number represent and what does that bottom left number represent. Once again, going to the review sheet. If you do not know, here it is. The top left number is the mass number. So I'm going to go back, and the mass number here is 19. Now, this one asks us for which of these represent the same element. So same element, keywords here, same element means same number of protons. Number of protons. So I'm going to look for that. I see 1 proton, 1 proton, 1 proton. And this one all the way at the end, this one has 2 protons, so this is different. So the answer for this one would be D, E, and Q, which would be B. Number 6. Which electron configuration represents excited state of calcium? So once again, calcium, I'm going to go look it up in the reference table. The electron configuration of calcium, I see it right here, 2882. So 2882, that is the ground state of calcium. So I'm going to go ahead and cross this out because this is the ground state. This is the ground state. Now I'm going to use the ground state and see which one of these represents that one electron jump to the next, because that's going to be the one that's the excited state for calcium. Now, I'm going to cross out the ones that change the number of electrons, because when an atom is in the excited state, one electron is jumping to the next energy level. That does not mean that the number of electrons change. It does not ever change. So I'm going to go ahead and cross out the ones that add up to a different number of electrons, which would be B and A. So that leaves me with C as the answer. In C, I see that, how did it go from D to C? One electron from the third shell went to the fourth shell, and that's why I have 2873. Number 7. This is asking for the mass number. The mass number is the number of neutrons plus neutrons plus protons. And it is right here. So let me write it over there on the practice test. Mass number is equal to number of protons plus number of neutrons. So if I look at this, they give me that information. They give me that it has 6 protons and 8 neutrons. I add that up. 8 plus 6, I get C. Going to the next one. Isotopes, which are a representation of the same element. Okay. I can easily cross out some of these answer choices because some of them have different symbols. So if they have different symbols, they're different elements. Let me take a look. A has N and it also has N, so I'm going to leave that one alone. C has N and it has Ne. These are not both the same. This is nitrogen and this is neon. So this one is out because it's the different elements. Same thing I see in B and D. So they're not the same element, so I cross those out right away. And I'm left with A, which is both nitrogens, same number of protons, different mass number, different number of neutrons. Let's go to this one. This one is asking another isotope question. Which are the isotopes in this table? We are given 4 different atoms. Right away, I'm going to look for the one that has the same number of protons. So that would be D and E. Same number of protons, different number of neutrons. And both check out. That is it. 10. This one is asking you from earliest to most recent about the atomic model. How did it play out? So what I'm going to suggest is go from the simplest to more complex. So the most simplest description to the most complex description. Here, the simplest description here would be this one, B. Hard indivisible sphere. And then we have C. Mostly empty space. And lastly, we have A, which is electron shells outside of central nucleus. This one is the most recent, while this one is the earliest. So the answer here would be C. Eleven is a tricky one because it's set out in a very complicated language kind of problem. So let's break it down. They give you a chart and they say that it represents subatomic particles, and the masses of the subatomic particles, they give it to you. They say X is so-and-so and Z is so-and-so mass. So I'm going to start drawing an atom, right? I'm going to draw this circle and this around the circle. So in this circle, at the center of any atom, we know that that is protons and neutrons. And that's located inside the nucleus. And what we have over here on the orbitals are the electrons. So that's that. Now, if we go back to the review sheet, if we don't remember the masses of these, I want you to ignore the numbers for now. I don't want you to look at the numbers. I want you to look at what's highlighted here on the bottom. It says, the mass of an electron is not counted in the mass of an atom because their mass is extremely small compared to protons and neutrons. Quote unquote, it's like spit in the ocean. It's not counted for. It's not relevant. It's very small compared to the rest. So the mass of an atom is really coming from the protons and the neutrons. So now, if you were to label these, if you were to choose one of these and say which one is the electron, choose the smaller one to represent the electron, right? Because we know that an electron has to be smaller than a proton and it has to be smaller than a neutron. Okay, so I take a look at these two numbers and I see that the Z must represent the electron because that is the smaller number. The power to negative 28 means that there's going to be more zeros in front of that 9. And so the X can either represent a proton or a neutron. So now looking at this, what this question is really trying to test you on is, do you know that an electron is smaller than a proton? Do you know it's smaller than a neutron? So if I go to A says X is a proton and Z is an electron. And guess what? That does agree with what we just discussed, so that is the answer. Let's go to 12. 12 is asking you if you know how to set up to determine the atomic mass of this example, which in this case it's lithium. So here, what you can do is you can go to the review sheet, and there are two ways to calculate average atomic mass. The one that we used in class is this one. We use this equation. So we took the mass of an isotope, multiplied it by the fractional abundance. So we converted that percent into a decimal and then multiplied it. So here you have an example of what we did in class. Then the next isotope, we did the same thing. We separated each isotope with a plus sign. So here you have that in the middle of those two isotopes. Okay, let's go back. So that is what I'm going to be looking for here. Let's look at them and let's see which one is converting the percent into a decimal. So this one is not going to be 7.6, it's going to be 0.076. Now, if you don't know how to convert a percent into a decimal, here's a reminder. Either one, you divide it by 100, or two, you move it 2 places to the left. 1, 2. And that's where your new decimal is. So in the first one, that's going to be 0.076. I see A does not do that, so I'm going to cross that one out. And I see that B does have that number multiplied by the mass. Cool, so that one has it. Okay, and now I'm going to look at the next one and see if that has that same setup. So converted the 92.4% into a decimal, that is there, check. Multiplied it by the mass as is, check. And that is my answer. Matches. So this is it. B. Number 13. This one is asking about location of subatomic particles. And if you look at them, we already discussed this back in question number 11. So the answer for number 13 is A. Protons and neutrons are located in the nucleus. 14. Bright line spectra. Okay, this is saying when is a bright line spectra produced. This only happens at a certain time, and that is when electrons move from higher energy states to lower energy states. So D. Number 15. Okay, once again, talking about the atom, the structure of the atom. So we discussed this back in question number 11. We said that protons and neutrons are found in the nucleus and electrons around it. So that means for 15, the nucleus must have a positive charge and it is surrounded by negatively charged electrons. So that one would be C. 16. This is very similar to the one that we just did, number 12. So they give you a percent and they give you the atomic mass. Then they move on to another isotope, give you the percent and the atomic mass. Okay, and which one is the numerical setup? So they're not asking you to solve it. They're just testing you on, do you know how to solve for this? So do you know how to set this up and put it on a calculator? Okay, so this one I'm going to look which one is making these percentages into a decimal. I'm going to cross out these that are talking gibberish, have nothing to do with the setup that we've seen before. Going back once again to the review sheet, if you forgot what we did in class, here we are. This is the formula that we used. Average mass equals mass 1 times fractional abundance plus mass 2 times fractional abundance of that second isotope. So we're separating the isotopes, the different isotopes that we see, by a plus sign. Let's go to the first one. Okay, so I should have, from here, I should have a 0.61. So that would be C. I find that in C. Multiply that by the 68. I find that in C again. Now I move on to the next. I see 70.92, just like in the problem, and I see the decimal turn into a fraction as well. So C is my answer for this one. 17. This is asking for the conclusion of the Goldfoil experiment. So Goldfoil experiment led to the conclusion that an atom is mostly composed of, and this is that most of the alpha particles went through, but some were deflected. So most went through, but some were deflected. The first part where it says most went through, the conclusion for that was, going back to the review sheet, because this is there, when most alpha particles went through, that told forward that the atom must be mostly empty space if most of the alpha particles went through. Since very few deflected, that means that there must be something in there, and that little something must be positive. So he said, atom has a small, dense, positive nucleus. So that is Ford's experiment, the Goldfoil experiment. So for this answer, that would be B. Mostly empty space and has a small, positively charged nucleus. 18. Atoms of, okay, so they give you examples of that, have the same number of, okay, I see the same symbol right away. If I see the same symbol, I'm talking about the same element. And if I'm talking about the same element, I'm talking about something must have the same number of protons. Same number of protons. So let's complete this sentence. Have the same number of protons. So we're stuck between B and C, but different number of, okay, and that would be B, because it's not different number of electrons. No. We're talking about an isotope, same number of protons, and they also have the same number of electrons. The only thing that is changing are the number of neutrons. Okay, let's go to 19. Which elements are in the mixture? Okay, so going back to the review sheet, it does mention an example of how to know which are in the mixture. So here we have an example. Okay. If you look at this bright line spectrum, you're comparing each element to the mixture. And if you find the lines of that element in the mixture, they have to be all the lines. Then that element is said to be in the mixture. So let's do it. Let's look at 19 and compare the lines from each element to the mixture. So for 19, let's look at A first. Okay. Let's see. There we go. Okay, so A. Oh no. No. Okay, A. Once again, A. All right, it's coming close. This line is present in here. Goodness gracious. We see this line is here. So that's the first line. The second line is also present here. Third line, present in the mixture. Fourth line, also present in the mixture. So I can say that element A is in that mixture. Now let's go to element D. This line, I already see these two lines are not in the mixture. So element D is out. Let's go to X. I see that these two lines right here, they're in the mixture. This line is in the mixture. This line, also in the mixture. You can't see it because it's covered up with that pink, but yes, it's in the mixture. This line also in the mixture. This one and this one also in that mixture. So I can say that element X is also in that mixture. And let's go to the last one. I can stop right here at the first line because that one is not in that mixture. So element Z is not in this mixture. So my answer would be element A and X, which would be C. 20. Each line in the spectrum represent the energy of, okay, so when is light being formed? That's the question. And that is when energy is released. So we can knock off A and B. And when is energy released? When it moves from a higher energy state to a lower energy state. So D. Number 21. This is another, which numerical setup can be used to calculate the atomic mass of the element chlorine? Once again, we're going to be setting it up. So I'm going to look for the ones that are changing this percent into a decimal and then multiplying it. So let me see that. I'm going to right away cross out the ones that are in its percent form. And this one over here, it even tries to confuse you. They start mixing up the isotopes. That's a big no-no. So if this is the information for one isotope, this stays together. If this is the information for another isotope, this stays together. And the one that I see that does that, it is answer choice C. Now, this next one tells us to calculate it. So now they are actually telling us to calculate average atomic mass. So I see the percent for 1. Let's do this one. They give me 40% of an isotope has a mass of 16. Okay, so I'm going to write that down right away. 40%, so 16, which is the mass, times the fraction, so the decimal form of that percent. Okay, so that's one isotope. And then they give me the other one, 60%, 18 AMU. So I'm going to put plus 18, so plus and then 18 times 0.60. Now, if you are confused once again of what are we doing in that problem, please go back to the review sheet that was handed out. This is the equation that we are using. Average mass is equal to mass times fractional abundance plus mass times fractional abundance. So we're keeping the isotopes separate. And once you put this on your calculator, you're going to get an answer of 17.2. Going to the next one, 23. Okay, this one is asking, explain in terms of electrons and energy states how the light emitted by excited atoms is produced. Okay, they want you to state, you can put this in your own words, but really what they want to hear is that you know that excited atoms release energy as they move from a higher energy state to lower energy states. That's the key words there. Once again, you don't have to put that word by word on your paper, but that is the information that they want to hear. That you know that excited electrons go from higher energy state to lower energy state, and that's when they form light. Okay? Number 24. For 24, they're giving you the electron configuration, and they're saying, why does it represent sodium atom in an excited state? Now you can say that the electrons did not change, so the number of electrons did not change, and some electrons went to the next energy level. You could also say the electron configuration represents a higher energy state than the sodium's ground state, and then state the electron configuration of sodium, which would be 281. You could also say a second shell electron has moved to the fourth shell. Perfectly fine. And number 25. This one is pertaining to a formula that we are not going to have the day of the Regents. We are not going to have this on our reference table, so we do need to remember it. Mass number is equal to number of protons plus number of neutrons. So we need to know that this right here is telling us something. It tells us the element, which is I, and it tells us 127. That 127 represents mass number. So if you did not know that, you need to write that down. Mass number. That is represented. That number after the dash, 127. So I'm going to start plugging it in. My mass number is 127, and it's equal to number of protons, number of neutrons. It's not given in the question, but the identity of the element is. So I'm going to go to the reference table, and I'm going to look for I. It's over here. And I'm going to circle the number of protons, which is 53. So I do know the number of protons. I just needed to look for it. 53. Plus number of neutrons. Okay. Now all I have to do is solve. So minus 53 on both sides. I get the number of neutrons is equal to, the answer is 74.